Ready for us? All right, fantastic. Boy, I just, I'm the luckiest guy in the world. I get to tell stories for a living. That's pretty much the job now. I don't do any real work anymore. Uh, the upside is I've been doing this for so long that 40 years of software development, for better or worse. I make a few podcasts. I think you folks know that, .NET Rocks listeners. Oh, wow. Okay, that's awesome. And I don't own the term geek out, but I did use it in a very useful way when Carl got me to do this thing. So we've been making these geek outs, which is just an excuse. I don't make as many as I used to now. This particular talk is derived from the worldwide power analysis. This show here, so the first version was in 2016, there. So this was a listener said, can you kind of explain energy? Like we've been doing all the alternative energies. I did solar and wind and thermal and so forth. And now this was like, how can we pull all this together and just talk about it as a whole? And then the same thing that happened to me with the space stuff was other conferences said, well, will you talk about this? And so I've done a few versions of it, but one of the things that's happened now is I've come to appreciate that folks like to hear about how energy works in their home, in their country. So how many Norwegians do we have in the room? It's all Norwegians, right? So I'm going to talk about the Norway power system in the context of what we're doing with power worldwide. And to me, it's hugely interesting. It makes the talk really fun for me because I get to study different power grids. I've done like 8 different countries now. And I'm from British Columbia, where we kind of got power like you do, which is to say a lot of mountains and a lot of water, so we make a lot of hydro. But what you guys are doing from there is super cool to me, and I'm happy to discuss that. But let's talk about the fundamentals and how we use electricity and how we actually go about making it with high tension lines and so forth. And for the most part, it comes down to the same thing. Right now, worldwide, we're at about 15 terawatts at peak consumption. That's a lot of energy all over the world. At 160,000 terawatt hours, or I guess we call it 160 petawatt hours. We would be the only room that understands what the heck a petawatt hour would be. And we do it by spinning motors, right? Or really alternators. Tesla's the guy who figured this out, the AC motor, and how if we turned it, it created, with 3 sets of coils, actually they use 6 sets of coils, this what we call 3-phase power. So the AC cycle was generated by spinning the turbine, and it's 60 hertz in North America because the Westinghouse turbine that was the most stable turned at 3,600 RPM. And it's 50 hertz in Europe because the Siemens turbines spin most stably at 3,000 RPM. No more magic than that, right? And that's how standards are made. Well, this one works, let's make more of that. And then you go to Japan, where the Germans sold the power system to the west side of the country, and the Americans sold the system to the east side of the country, so they have both, which is why they make switching power supplies, because they had the problem, and we have all benefited from that. The vast majority of those generators are turned by steam turbines. This is very refined 100-year-old technology now, where we take as much energy from steam as we can possibly get. We pressurize the steam. Water boils at 100 degrees centigrade, but we pressurize it so we can get it to about 300 degrees, which gives us a lot more energy. And then we pump it through this massive turbine. There's several stages in this. The high pressure stage is right here, so the hottest steam hits here. And then it'll go through an expander to the mid-band, which is this set of turbines, and then to the low-pressure turbine. And that's all about taking the energy that's in that steam and extracting as much as you can from it to spin that generator at either 3,000 or 3,600 RPM, depending on which generator you're using. The advantage of this is the amount of kinetic energy it has when it's spinning. So one of the things you can do when you're switching power sources, so you're boiling water somehow under pressure, then you're pumping the steam to this and spinning it. Now you need to do work on the boiler. So you light up another boiler, get it up to speed, and then you switch. So the way you switch is you simply turn the other one off, the steam stops, but this thing keeps turning. It's got a lot of momentum, and then you have a couple of minutes now to get the other steam flowing into it, and you just continue generating power. That's what we've been able to do. This is 100-year-old technology, and it's reliable, it's very well known. It's why we just expect our PowerPoints to work, to the point where you forget all of the magic that goes into that. Now we got to talk about how we're changing it, because we're changing it for a lot of good reasons. But that mechanism is not going to be the mechanism for all of the power we generate these days. The usual way when we have to compare energy sources is we use a thing called LCOE. So this is the levelized cost of energy. So that's how much does it cost to build the power plant? How much does it cost to operate the power plant? How much does the fuel cost? How long does it last? How do you clean it up? Hopefully you included that in the math. That, and how much energy will it produce over the lifespan of that power plant, divided by the number of megawatts, is the levelized cost of energy. So that's a way for us to provide a measure between all these different power plant systems. Now, for better or worse, Norway's power grid is somewhat, tough terrain, but the people kind of live towards the coast for the most part, so that's where you've run your wires, and you're got mountains, got water, hydro. So we're gonna, spend more time on hydro, but I want to run through all the major power sources and roughly their costs, and then we'll talk a little bit about the role of it. So let's start at coal. You had one coal power plant. It's in Svalbard, which is also where the coal mine is. How useful. That power plant's now closed. You've replaced it with a diesel power plant. We'll talk about that. But you still got the coal mine running, at least for a little while. You're selling it to other people. Coal runs somewhere between, this is all US dollars, $65 to $150 per megawatt, levelized cost. Typical lifespan of a coal power plant is 40 to 50 years. These are largely falling out of favor because coal continues to get more expensive. It's also the most lethal way to generate electricity. More people die per megawatt by coal than any other way. That's miners being killed, that's operators being killed. Coal explosions are a business, they're very serious. That's the poisoning that happens shipping coal from the mines to the plant, as well as the effluent that comes from the plant, causing cancers and killing others. Generally falling out of style. When coal started in the 1750s in England, it was called the savior of the forests. It was the rock that burns, because up until then, if you needed heat to cook food or keep your house warm, you cut down a tree. But then they found the rock that burns, and it was going to save the forests. We know better now. Oil power, pretty much out of business. This is not there's better ways to use oil, but once upon a time we used to spray it into a burner to boil water to spin a turbine, same way we do with coal. There are no oil power plants in Norway. There are a few in less developed parts of the world. So not a great way to make energy. It's expensive. $75 per megawatt is pretty pricey. Obviously, oil and gas has a role to play in Norway. Is your largest export by a non-trivial amount. There's a bunch of oil gas people sitting in the front row here ready to heckle me. Join in. And you're now the largest gas supplier in Europe because somebody else went offline. Anyway. Yes. If you're going to burn a petrochemical to boil water to spin a turbine, the way to do it is the combined cycle natural gas plant. These are still pretty popular. They're cost effective. Running in about $45 to $75 per megawatt. So on the cheaper side, they're very inexpensive. The reason is, and this is the combined cycle part. So here's how this thing works, is they're quite small, relatively speaking. This is an air box. So the air comes through here and is filtered. This is the turbine. So there is a high pressure turbine like a jet engine that the natural gas is pumped into and burns at very high temperatures and speeds, and that turns a generator. And then there's an expansion box here to a steam turbine. So now they take the residual heat that comes out of that jet turbine, boil water at pressure, and spin another turbine with it. Combined cycle. So the amount of energy they get per ton of carbon dioxide is the highest. It's quite a powerful way to go. You have a handful of these that you don't appear to be using. So mostly they were built to burn gas that you couldn't sell at a reasonable price to operate oil fields. So Karstow, Mongstad, all similar. There's one higher up in the north. It looks like they built it and then never actually used it to generate electricity. It's fun to have money, isn't it? I'm not used to seeing this in different parts of the world when I look at it. It's like, you built this plant in 2015, you turned it on to make sure it worked, and then you turned it off. 150 megawatts. All right, good enough. There's only one combined cycle plant, and that's the one in Karsto, and it's actually being dismantled now. It was about 400 megawatts. Nuclear power. You've never made electricity with nuclear power commercially in Norway. You do have a handful of nuclear power plants. Now, this is still the same essential mechanism as opposed to burning coal or oil or gas to boil water. You find really weird rocks, and you purify them and put them close together, and they boil water. And you keep them under pressure till you get about 300 degrees. You go through a heat exchanger so that you don't use the radioactive water in the turbines, and you spin turbines. That's how this works. That's the light water reactor. We could get into other models, but it's fairly far off the reservation. There are only 4 nuclear power plants in Norway. They are all decommissioned now. They were all research plants. They experiment with different technologies. The very last one to be shut down, which is the Halden boiling water reactor, did an experiment from 2012 to 2018 on using thorium in solid fuel. Thorium is the lowest of the actinides. It's the lightest radioactive element as opposed to uranium, which is somewhat heavier. It's 5 times more plentiful than uranium, so there's always been an idea that we could build reactors with this more plentiful material. And so they actually did a set of tests at Halden to run those as fuel rods. There's a bunch of problems with doing that, but it was an interesting experiment that has ended. And now they're in the process of cleaning those plants up, which will take decades. Radioactive materials are tough to work with. You try not to kill people while you do it. There's really no reason to use nuclear power in this part of the world, but we'll talk about the modern approaches to nuclear as we go further down the path. I'd be remiss not to talk about biomass as a power plant. So this is taking agro-waste and burning it, again, to spin a turbine, to boil water and spin a turbine. Why do this? Because you have it. So typically, these are small plants, a megawatt or two here and there. You make about 140 megawatts total in Norway across a couple of hundred different plants. So where you're growing things, you have agro-waste. And one of the things you can do with it is turn it into electricity to run the agricultural facilities. Power distribution is very localized. It's just a good way to use up the waste. There's more efficient mechanisms here. They are somewhat polluting, but you were going to release that carbon anyway, right? You take the leftovers from making pulp. If you bury it in the ground, it's going to release carbon. If you burn it, you make energy and you release carbon. So it's kind of a trade. It's just a thing that we do. You don't do this at scale. Geothermal power. Now, this is a really cool thing if you think about it. I drill a hole into the ground to where the rocks are really hot. I send water down there. It comes back with a whole bunch of energy in it. I spin a turbine, I cool it back down, and I pump it back down again. Really no emissions from this whatsoever. The problem is the hole drilling part. The longer the hole is, the more expensive it gets. And so it's only where the hot rocks are close to the surface that it makes a lot of sense to build geothermal power plants. Go visit Iceland. Their rocks are a little too close to the surface these days. I don't know if you've noticed, but it's kind of hard on fishing villages. This technology is evolving a lot, actually. I did a whole hour on geothermal power if you go look for the Geek Outs on .NET Rocks. And I think I did a good enough job that the Geothermal Society asked me to come and present. It's like, I'm not actually a scientist. I'm just a storyteller. He's like, we really like the way you tell stories. The hard part here is that, yes, drilling holes in the ground is hard, and the oil and gas industry are the best at it. In fact, what's happening to geothermal power now is a bunch of the technology that was developed for fracking is now being applied to geothermal power so that they can drill horizontally. So they find a bed of hot rocks relatively close to surface, 2-3 kilometers down. Then they'll drill beside it and come underneath it horizontally, and then they'll fracture that rock so they have more room to pump water in there that'll immediately heat up, and then they drill draw holes above that bed so the steam comes up through there. Now, why is this better? You get more yield, so you're going to collect more energy, but one of the things that happens when you keep slamming cold water into hot rocks is the rocks get grumpy. They shatter. They create little earthquakes and things. And sometimes the water doesn't come back anymore. And so the expensive part of your geothermal power plant just stopped working. But if you're doing horizontal drilling, you can still use the down line. So where you drilled in by the side, you can use that line and now drew new feeds across into the bed again and possibly relight it. So these are experiments being done in America right now. Google's actually driving a bunch of this. They want to use geothermal power to run their data centers. And so they have a 5 megawatt pilot plant now generating electricity based on this methodology. One other thing, which feels more science fiction, but I have seen it, it is real. Instead of drilling the traditional way, the oil and gas way, which is with diamond tip grinding bits that you have to replace because the rock is really hard, and then you keep pumping fluid in to keep them from overheating, and have to pull the material up as you drill, which is expensive and time consuming. Is why drilling is so hard. There's a group of scientists that built a microwave-driven driller. So they use 9 gigahertz microwaves at the end of the head to vaporize the rock into plasma. Like this is Star Trek. So, and then which naturally lines the walls of the hole as they're going down with vitrified rock, and they can just keep on drilling. There's no pressure necessary, no pressure management needed for that, and the hole is self-sealing. It's a lot of energy, like to run a microwave like that, but it's another way to drill that opens some possibilities for what can happen in the future. More geothermal power would deal with a lot of issues. They tend to be smaller plants, which we're getting better at. They're localized to the ground around them. If they're maintainable, their emissions are tiny. Their explosion risk is 0. There's no pressurization here. Like, for the most part, they're very, very safe. So we could do with more geothermal power. We just got to get more reliable technology for it. Diesel electric. All right, you've just built one in Svalbard. These show up where I didn't even mention the cost of these. When they work, they run in the 50 to 90 megawatt range, so not as cheap as combined cycle gas, which is also stunningly reliable, even though it's got emissions. The geothermal is a bit more expensive than that, and it can be much more expensive than that. But it can, when you're planning on a 50-year lifespan for your power plant, and then one day it just stops working because the water doesn't come back, that's why people are afraid of building these. So diesel electric, you only do this where you have to. Islands, places with a limited population, limited number of resources, no natural way to generate electricity, see Svalbard. Right? So what they're committing to give up coal is ships coming routinely to fuel basically a giant diesel motor. When you don't have to move the motor around, because we always think about trucks when we think about diesel motors, but if you don't have to move the truck around, there's a few things you do differently. A, the gas tank's really big and underground, but so is the oil reservoir. So they use a massive amount of oil so that they don't have to do oil changes per se. The oil just keeps cycling through, and occasionally they draw some off and replace it with new. They're designed to run 24 hours a day, very stably, but they're stunning. They're small, 10 to 20 megawatts, not the 400 or to a gigawatt that we get from modern power plants. $400 to $600 a megawatt, like just very expensive ways to make electricity. But there are few options in some of those places. And Svalbard is one of those challenges. And they're not the only ones. If you go down into the Canary Islands, mostly run by diesel. It's just what happens there. All right, hydroelectric, maybe you've heard of it. Inexpensive, $40 to $50 a megawatt, mostly because of extremely long lifespans. 100 years for a hydroelectric plant is normal, right? With maintenance. They last a long, long time. They count on a simple truth, which is that I have a high altitude place and I have a low altitude place and water in both. So as long as there's water coming from above, I can capture that energy as it falls, right? The potential energy is the altitude of the water. 1,769 hydroelectric power plants in Norway. It's 88% of your electricity. You got mountains and you got water. But that's the weakness of these. Sometimes you don't have water. So, you're capable, you've got the largest hydroelectric system in Europe, and you're capable of producing 156 terawatt hours per year. That's a huge amount of electricity if you have enough water. So you have already had years where you've had to dial back using hydroelectric because it didn't rain enough, and the reservoirs don't stay full. So we've always thought that when you just presume that nature was unmovable by us, the hydroelectric dam would run forever, but we're already finding the issues. And this is true in British Columbia, where we have mountains and lots of water most of the time. And so we're able to make most of our power in this zero-emission way by just using the gravity of water as long as it rains. And so now we have to start looking to alternates, but it turns out we can do more with hydroelectric power. We can also use it as a storage mechanism. You can pump the water back uphill. Largest hydro complex for you guys is Ullafjord. I love pronouncing Norwegian words. But what's cool, what I like about that, looking over the setup, is it's actually 3 different power plants using the same water, stepping down over distance. So, getting a lot of electricity that way. Okay, I've talked about mostly traditional power systems. Let's get into the newer stuff and we'll talk about wind. Why is wind so popular in a lot of parts of the world? Your neighbors to the south, the Danes, have a ton of it. Cheap. In 2023, you're talking $25 per megawatt LCOE. That is inexpensive. It's a race between who's cheaper, wind or solar. They're both getting stunningly inexpensive. As of 2020, because the numbers are hard to get newer numbers than that, you have some of the largest wind setups around, and you've got some of the biggest offshore. So we got to break these into multiple categories. Onshore being the big one. It's easy to build. You generally put it in places where folks aren't around, although you are running into issues with the Sami, as I understand. I got to do a lot of reading. Mostly doing translated Norwegian stuff, because it wasn't actually published in English. So listen, I'm from Canada, where we have mistreated our indigenous people for a long time, and we're trying to do stuff about that. I feel for you. It's hard. It's hard to try and do the right things. But it's 11% of your electricity, which is about 5 gigawatts of production capacity. So if you're doing the math, 88% hydro, 11% wind, and you have about 1% left, which is the biomass stuff and Svalbard's solutions, such as they are. But this is for the most part, what you're doing. And the on-land stuff is great. It can only get so big. There's always, folks talk about bird strikes on wind turbines. One of the complaints about it. Just to be clear, the current estimate as of 2020 was about 500,000 birds a year died of bird strikes on wind turbines, as compared to 2.5 million killed by domestic cats. If you want to protect birds, keep your cat inside. The University of Virginia put a camera on like 50 cats to watch what they did when they were outdoors. Not all cats kill birds, but the handful that do are psychotic. They kill everything they can find because it's fun for them. So yeah, if you kept cats inside, and by the way, you think cats are bad? Current estimate for bird deaths due to window strikes on buildings, $4 billion a year. Don't worry about the wind turbines. That's not the issue. We have much bigger issues around that. That being said, when you go offshore, there is thought when you place wind turbines offshore to try and position away from migratory paths. I mean, it's one thing to kill the birds, but it also damages the turbines, and that's a bigger issue. So they do try and position them. Now, we tend to call this near-shore placement. So these are wind turbines that are actually embedded into the seafloor. It's good to, you only do that up to about 50 meters. There's some concern about the damage it does. In order to do this, you build a casement, so basically a big steel tube gets put down to the seafloor, the water's pumped out, then in comes an auger, drills a big hole into the seafloor, then they pour a whole lot of concrete, put the mast in that wind turbine, right? Ask the Danish, they've done this a lot. They have lots of shallow water, just the stuff you don't have, right? 50-meter water almost doesn't exist in Norway. If you're in the water, it's deep, right? They call them fjords for a reason. And I relate, British Columbia, the same thing. We have no wind turbines in the near shore because once you're a kilometer off the shore, that's 200 meters of water and going down. So there is developments now into floating wind turbines. So this is straight out of the oil and gas industry. You know it better than ever. This is one of the Eleanor designs. It's way more complicated than you realize. They cable stay them, try and keep them in place. Each of those columns are actually ballasted. They shift the ballast to counter motion, including torque from the wind turbine itself. The upside to offshore is substantial. You can build them far bigger, the largest wind turbines in the world, that larger wingspans than 747s. One rotation would power a house for a year. That kind of scale, 10 gigawatt turbines, all offshore. They're far enough offshore when you can get into deep water like this that nobody sees them, lowers the complaints. The downside is the electricity is not needed there. So you do have to run cables back to shore and deal with all of those challenges, and that costs money. However, so this offshore stuff is more expensive. It's not as cheap as the nearshore, as the onshore stuff, but has huge advantages. The wind is stabler out there, blows more often, it's very consistent. We get decent lifespans out of these now. We are dealing with the challenges of replacing turbine blades and what to do with turbine blades, so they're becoming more recyclable. But that's all because we've been building far more of them and getting better at establishing that industry. So Norway leads the way on this. They've done a lot of the most interesting construction there. The Hywind Tampen offshore farm has been in operation since last year. It's not huge, it's only 11 turbines, which makes it very expensive, but the nice thing about the wind turbine system is that once you get the license, you can build the initial plan and make sure you've got everything working, and then you just keep adding to it. And then the cost per unit starts to go down more and more and more. That being said, none of this power is being consumed on shore at all. They mostly use these offshore turbines to run the oil platforms. So instead of burning fuel at the platforms to run generators to make their electricity, a portion of their power is now coming from these large turbines, about a third at this point. But if that's only 11 turbines right now, they scale it up to about 40, that could be all the power they need for those platforms. One other class of, I'm going to talk about solar, but I should talk about all of solar. Let's talk about heliocentric solar. So this is not the solar cells you're thinking about. This is heliostats, mirrors, all aimed at a central point. This is actually a 2 gigawatt plant in Morocco where they got a lot of sunshine. And they focus all that light into that central pillar in the at the center where it gets white hot. And they pump fluorine salts. They get up to about 800 degrees centigrade. It's liquid between 400 and 1,000 degrees, and then they pump that to turbines to spin turbines. But one of the upsides to using those high temperature salts is they get so hot, they last through the night. So it's actually a 24-hour day power plant. The problem is you need a lot of sunshine, and they're really quite expensive, 120 to 150 per megawatt LCOE. Why? All those mirrors are continuously moving. They're tracking the sun to keep it on the mast. They all have 2-axis motors on them, and they're in the desert. And motors don't like desert. And so you have a team of people ranging over the kilometers that cover this, constantly repairing those motors. That's what drives up the price of operating this. It seems like the ideal power source. 24 hours a day, working with the fluorine salts, running turbines very reliably, except that it's expensive to maintain because it's just tough conditions for making electricity. Commercial electrical solar is the cheapest power right now. The current price is coming in about $23 per megawatt. It's back and forth between wind and solar these days. The reason is largely the Chinese started mass producing these 22% efficient cells a few years ago for their own use and sold them to everybody else. Just the scale of the manufacturing drove the price down. We could have done this years ago. They're the ones who actually did it, for better or worse. But this is a process of capturing electricity directly through the silicon. It's manufactured much the same way you make CPUs. It's one of the reasons it could scale so well. Typical lifespan for solar panels about 20 to 25 years of this particular species of panel. They lose about 2% efficiency per year. The temperature matters. The hotter they get, the worse they get. So solar panels in the desert are not good. They don't last. It's too hot. Temperate zones do better. You don't do a lot of solar in Norway, and the reason is land. You don't have these big flat spaces to waste. Where you got them, you grow food, and good on you, because eating's fun. I do it a lot. But you do cover your roofs in it. So commercial buildings covered in solar panels are pretty common. They're not as cost effective, so super cheap to do those huge panel arrays down on flat land. But as soon as you put them on roofs, every one of the installations is different, and the price difference is almost a tenfold, 150 to 200 per megawatt. But that's kind of a funny number because you never install a megawatt. You install less than that. Roofs are only so big, and for the most part, that power is consumed by that building. So you're localizing distribution. If you can take a commercial property off the grid effectively, several hours a day, several months of a year, it makes a huge difference in the grid overall. Yes, there are buyback strategies. They have a limited amount of utility. Electricity does not flow like water. It's not fully bidirectional. It cannot be stored easily. So the buyback stuff is largely political to make these installations make sense. There is a little bit of sharing that happens, but that's not the reason to do it. The reason to do it is to take the pressure off the grid by being able to supply power at certain times of the day and year. We're 60 degrees north here. I live in a place that's 50 degrees north. It gets dark, except in the summertime when it doesn't get dark. And they don't need perfect sunshine. They work better than you think. In theory, the sun represents about a kilowatt per square meter of energy landing on the ground. And realistically, we capture maybe 200 watts of that per meter. And then when you deal with weather and things, it's about 100, 150. If you get to 200, it's a good day. We're getting better at the controls around this to get more yield from it. All concentration strategies you try, where let's put more solar by focusing it or using reflectors and so forth, tends to overheat the substrate, which reduces efficiency and lifespan. So the reason we do it this way is to keep that price down. Same for rooftops on your house. Yeah, we've done roof solar tiles like our friend Elon has, although largely that's been a failure for a couple of reasons. One is it's far less efficient. It's far more complicated to install. It has lifespan problems. And for most people, putting solar on your roof is virtue signaling anyway. Like, I'm going to go all that trouble and not make it apparent to people? No, give me the ugly ones. Let me see it. There's lots of efforts going on in solar to try and get better than the 22% that comes from silicate substrate, this particular approach to photo solar. And you've probably heard some of these in the news, like perovskite. So perovskite is an organic crystal approach, and it has yields in the 30% range, which is pretty exciting, except as soon as they get hot, they start losing efficiency. And the lifespans are low, like less than a year. So great in the lab, bad in the field, not a product. Doesn't mean we're still not working on it. Like, there's lots of smart folks trying to build them better, and so make them more reliable to last for longer. Okay. LCOE is very unfair when we talk about solar and wind. Why? Because all the other power systems we've got that we talked about, we have complete control over. You decide how much gas to put in, how much coal to put in, how deeply you put your control rods on your uranium to make as much electricity as you need at the time. In fact, your grid was designed, and all those people that work really hard to operate the grid are about making exactly as much electricity as you need at the time. That's the way the grid has happened for 100 years, and only in the past 20 or so have we messed with that model, because these power strategies, both solar and wind, don't comply. They don't generate when you need, they generate when they can. And that actually destabilizes the grid. The grid's getting better at dealing with that. And so one of the approaches to dealing with that problem of I don't have power when I need, I have too much at certain times, is to try and store it. And once again, our friend Elon pops up with taking the designs of the batteries that he used for his cars, which have been very successful. I see a few of them around this town, oddly enough. And making them into stationary battery packs. So excess power available, stored in the battery. Not enough power available, discharged from the battery. They're expensive. And the lithium-ion battery design is wrong for this application. Lithium-ion are light relative to the amount of wattage they can store. That's why they're good for cars and phones and things like that. They also can charge rapidly and discharge rapidly. All features great for a car, not needed for the grid. The natural discharge cycle of the lithium-ion battery is about 6 hours. And so typically in a grid scenario, you need power for longer than that. But the upside to what Tesla's done by maturing this to the point where the Australians are running a bunch of it, they got some in California and a few other places, is that it's made a market for grid scale battery storage, but we're switching technologies to things that are better suited to the grid. One of them is Form Energy. So this is actually from Matteo Jamillo, who used to work for Tesla, and he left to make batteries for the grid. His preferred battery design is actually a NASA battery called the iron air battery, storing energy in rust, which is messed up, but it's cheap, 1/10 the price of what it costs for lithium-ion batteries. The downside is it takes up more room, it's heavy, and it's hot, none of which matters if you're building grid storage. And the natural discharge cycle of an iron air battery is 100 hours, not 6. So now you're talking days of power to discharge on a normal discharge rate. Charge is slower, discharge is slower, but fast enough for grid applications. So they're now actually broken ground on this. They've been talking about it for forever. There's the site the furthest along to being operational is in Minnesota. They also have projects in Virginia, Texas, and Georgia. So it's purely been a U.S. initiative so far for a U.S. company, but they're becoming real. But you guys already have batteries. The smart Senja packs up in Senja. So this is the big island up in the north. I did not know this. I learned about this week, okay? And these are battery packs from the German side of General Electric, which confuses me. They've actually replaced them twice now. They've been experimenting with different battery technologies, but it's the Senja, for better or worse, is sort of the end of the grid in Norway. That's the challenge of being on an island. So they have the most power problems, and they're using these batteries to bridge between it. And it's helping in their fishing industry and things like that. So you're there, you're using it in a very specific application. Because I think for the most part, we're coming to the conclusion that batteries are probably not the solve here. That the better way to store energy is pumped hydro. So basically running a hydroelectric dam backwards. Instead of letting the water fall down and spin the turbine and make energy, we power the turbine to pump the water back up into the reservoir. The Australians did a massive study a couple of years ago where they showed geographically all over the world that pumped hydro could do most of the power storage for you. The problem is that hydroelectric plants need water supply at altitude as well as a place to put it below. And there are fewer of those. There are places where you have water below and a high slope. Because if you're just going to make pumped hydro, you can build a reservoir at the top of the mountain. You don't have to have water flowing into it already, and then you just pump water up there. The advantages of pumped hydro is they're quick. As soon as you have excess electricity available, you can turn on the pumps, start running the water uphill. When you don't have enough power, you literally let the water fall back down, spin the turbine, and make the electricity. It's about an 85% conversion rate, which is decent. The more important part is hydroelectric technology is completely known. The power industry is very conservative. They want to do 50-year projections on stuff. Well, you can do that with this technology. So we've pretty much demonstrated that the combination of intermittent power sources like solar and wind with enough pumped hydro can do a lot. They're always going to want a certain amount of baseload. The question is, what are the emissions of that baseload? And none of the unemitting energy sources can work as baseload with the exception of geothermal power and arguably nuclear, but we'll talk about that more further on. But this technology, you already use it. There's a ton of pumped hydro, mostly modified existing hydroelectric plants, where when you have excess energy, you pump it back uphill. Norway doesn't do this much, but other places that have a lot of pumped hydro are starting to put solar panels on the reservoir to make even more electricity. The solar panels are cheap. They like being on the water because it keeps them cool. They slow the evaporation of the reservoir, which is useful. And they don't work when it's raining, but the reservoir is filling up anyway, so that's fine. And when it isn't raining, you can use that power to pump more water uphill if you want to store more. So it's a good combination, right? And I think you guys will get there. It's just a question of how far you go down this path. The Portuguese have done a ton of this. They got about 800 megawatt pumped hydro solution in the northern part of Portugal, and they've covered the whole thing in solar panels. It's almost a self-referential loop now. All right. I would be remiss if we don't talk a little bit about hydrogen, which is another way we're talking about what to do with excess power and various forms of what to do with the hydrocarbons that we have. This is a very popular topic in Europe, for better or worse. It's less popular in other parts of the world. So most hydrogen gas today is made by refractoring petrochemicals. They already have the hydrogen in them. You can do a bit of chemistry to break it apart. And that's the gray hydrogen approach, and it has carbon emissions. Then we have this idea called blue hydrogen, which means we're still going to do that, but we're going to try and capture all the carbon dioxide. And then there's the version of green hydrogen, the one everybody wants to talk about, which is I put electricity into water. You've done this in your high school or your science experiments. Separate that water into hydrogen and oxygen. No emissions. Beautiful. Let's talk about the problems. So our known mechanism that is used the most is what we call methane steam reformation. So this is pumping a bunch of energy in to effectively burn that hydrocarbon, methane, yanking the carbon off and combining with oxygen to turn to carbon dioxide and getting the hydrogen away separately. It's efficient, it's fast, it's more than half of all hydrogen produced on the planet, for better or worse. Every ton of hydrogen you make this way produces 9 to 12 tons of carbon dioxide and consumes about 6 megawatt hours of electricity to do it, right? This is the baseline. It's a serious emitter of carbon dioxide. A more advanced form of this is the blue hydrogen approach. Is called methane pyrolysis. So now we up the energy consumption. So now we're consuming about 10 megawatt hours, so that we make a ton of hydrogen gas from that, and we get 3 tons of solid carbon. We're running at a high enough energy level the oxygen doesn't bind to it, and so you get graphite out the other end. Stuff you can bury if you want. It's just far more energy intensive, and it runs very, very hot. It's a challenging industrial plant to work from. And then there's the one you want, the green hydrogen approach, which we got about 4% currently being made in the world this way. 1 ton of hydrogen makes 8 tons of oxygen in electrolysis. You can do what you want with the oxygen for 40 megawatt hours. So 4 times the power of what it takes to do methane pyrolysis. It's just so energy intensive to make hydrogen this way that it's not cost effective. So that's why it's just not grown, because it's expensive. Where this gets interesting is when you start talking about excess electricity. Like the electricity that would have otherwise been wasted, maybe you could do electrolysis and just make hydrogen with your excess energy. The problem is that these systems don't actually start up that fast. So you need a larger window of excess power to make it make sense. Better to spin motors and pump the water uphill, which you can do in an instant, than it is to do this. In general, power storage falls into an array of bands. There's lots of different approaches to how do we store energy. In this graph, we're talking about more energy storage across the bottom and more storage time across the side. So capacitors can't store a lot of power, and they can't store it for very long. Batteries sort of in the middle there. Your pumped hydro, it seems to be the most advantageous, and throw on top of that the reliability of it. Hydrogen represents an excellent way of storage. It's very dense storage, but it's very energy intensive. So it's costly to do. Meantime, our cost of power has changed substantially. Coals continue to get more expensive. Geothermal's really not moved all that much. Nuclear is very expensive for a variety of reasons, and solar and wind have fallen off in the past 20 years to make a huge difference in our ability to produce power. That being said, using our world in data, you can still see that oil, coal, and natural gas represent the bulk of energy generation on this planet up until at least 2021. The IEA announced this year that a third of all energy production was now in non-carbon emitting. You know, the argument is we're about a third of the way along to what we needed to get to by 2050, which means we're well behind. But when I'm talking to young people about this, they're mostly despairing that we're nowhere. And just to tell you, we have really made progress on decarbonizing energy generation around the planet. We have. You know, back in the Kyoto Accords in 1998, the estimate for what was going to happen if we did nothing by 2050 was 4.5 degree increase. That will not happen now. We've already moved the needle enough that if we stop doing anything right now, we'll get to 3 degrees, which is still a catastrophe, but less of a catastrophe. I'd only say that to say we're making progress. We just need to do more and keep moving along on these things. And we're not going to make a degree and a half unless something radical happens. It's going to be somewhere in the 2s, which is very bad. But it's not, you know, and be clear, not bad for the planet. The planet couldn't care less, right? Bad for us. Now, admittedly, we live in the wealthy western part of the world, so we'll be the least impacted. It's the less developed parts of the world that suffer the most, and we have plenty of climate refugees, and that's a different talk. Let's talk about the newer technologies coming down the pipe, and I'm going to go back to nuclear because in certain parts of the world, this is a great solution. The problem with nuclear power in the existing form that we do it in is that each of these plants is bespoke. It's why it's so expensive. Every reactor is distinct. Every site does all of its own operations. So fuel rods come in from a factory elsewhere, typically made by General Electric or Siemens, brought in, they're then assembled on the site to build a fuel core, about 50 tons, and then the reactor is opened, the old core is removed, and a new core is put in. And over a course of a year, several times the reactor is shut down, the cores are shuffled around and reassembled. All of that very dangerous, high radioactive handling is done at the site. If you're going to do that, you need very skilled people, you need an incredible amount of regulation and certification, and you need a huge space. You got to keep people away from this, because if you make mistakes in fuel handling, it's very serious. And it's why nuclear is not popular, because it's frightening. And we've had a handful of disasters. That being said, it's killed very few people compared to any other method of making power. But there are more modern approaches now that are being developed and are close to actually being implemented. So the idea is this. Where we use the power, we don't do fuel handling. We just make the electricity there. So we make the reactors modular. We make them smaller, 300 megawatts. The operation site has a series of tanks that you put the reactors into when you operate them from 2 years. They're assembled at a protected site for skilled people. And then the entire reactor is shipped by truck into the site and out again. Now, this is not that weird. We already ship fuel assemblies this way. Now what you're doing is shipping all of the radioactive parts, all of the dangerous stuff, already assembled, brought to the site, run for 2 years, then removed, shipped to a processing site. So now all your skilled people and careful regulation, so forth, lives in one place, away from everyone, supporting multiple power generation locations. Here's the more important part that I think this crowd gets better than anything else. You replace the reactor, the entire reactor, every 2 years, which means upgrades. The key part of what happened to Fukushima actually had 6 reactors. You didn't hear about reactor 5 and 6. You only heard from about 1 through 4. Right? 3 was off, 1, 2, and 4 all had the explosions. Why? Because they didn't have passive shutdown. Why didn't they have, and 5 and 6 did have passive shutdown. Why? They were built 3 years later. TEPCO, when the passive shutdown option came along, said, we don't want to shut down the reactors for 2 years to refit them with this when they've only got another 5 years to run. Not worth it. Then tsunami. Right? And we put our emergency backup generators in the basement where the water is. Anyway, the point is we have passive shutdown reactors. They can be very safe. And we just got to build them that way. And if we keep them smaller, when they're down to this size, they actually don't have enough thermal mass to melt their containment anyway. And more importantly, you keep making better reactors over time. So this technology is being built by GE Hitachi. There's in Ontario, Canada, which gets 80% of its electricity from nuclear because they don't have mountains, and they don't get enough wind, and they don't get enough sun. They're now replacing their old CANDU reactors with this technology. So they're in the process of doing the first installations. They're a couple of years from first light, from actually running it. But same thing. Now, the Darlington site where they're going to do this installation, no fuel handling there. All the dangerous stuff is done further away up in the shield. And then it can do the continuous upgrades. All right, a little bit of fun, the last few minutes we've got. Let's talk about fusion. This is a picture of ITER. Except this one's assembled. ITER is still not built. It's only been 20 years. What are you in a big hurry for? And ITER, even if it works perfectly, will not actually generate electricity. It should maybe be somewhat positive. Trying to recreate the sun is hard. We're trying to do it with magnets instead of gravity, because if we did it with gravity, it would hurt people, so we don't do that. But ITER is also using niobium-10 superconductors. This is the same stuff that they use at the Large Hadron Collider, and there are better superconductors. So over in America, Commonwealth Fusion is using REBCO superconductors. So all those videos you've seen of the little cube floating over the liquid nitrogen, that's a REBCO, or a ceramic superconductor. And they're superconducting at liquid nitrogen temperatures. The problem is they're not a metal, so making them into wire has been extremely difficult. It took, those ceramic superconductors were found in the 1980s, and only in the past few years have they learned how to make a ceramic flexible tape to make coils from it. Commonwealth Fusion, partly funded by Bill Gates, but it's out of MIT, they've built 1 plate of the 8 plates for the reactor about a year or 2 ago and ran it at full potential. The magnetic field is about 5 times stronger than what's possible with niobium-10, which should be able to offer better containment. Smaller reactor, more efficient. So now you haven't heard from them, and let me tell you why. The only time you hear from scientists is when they need money. That's when they publish papers, and if you read the paper, it always ends with, further research required. I need money. Have you heard from Commonwealth Fusion? No, because they got money. They're busy building right now. Is this going to work? No idea. If I had a fixed amount of money to solve all the energy problems, would I spend it on this? No. Because we have known technologies we can do today that would make a difference by 2050. We do not know when this will deliver electricity. I hope it works. I want it to exist. This would make me happy. But if I was actually responsible for trying to reach the goals of the Paris Accord, this is not how you do it. This is still experimental. Now, we have enough money in this world to do all the things, right? We should be spending more on pumped hydro and low-emitting energy and moving faster on all of this. That doesn't mean we couldn't also still do this. But am I going to wait on this to solve the problems we need to solve in the next 20, 30 years? No. Just keep going, guys. I hope it works. It'll make a difference someday. By the way, machine learning comes into play. These are machine learning models for plasma management. They're going to start using a neural net to manipulate the field to better contain the plasma, because it's been part of the problem making fusion work. So some of the stuff that we're doing today is playing in new energy. Down to the last few bits. Let's talk a little bit about a modern grid. So the electrical grid was built to be a one-way thing. Relatively few large power plants generating very consistent electricity with serious emissions, being available at all your power points at all times. Enough redundancy that if a plant could go down or be used for maintenance and you still had electricity. Flexibility enough that when the football game is on and everybody puts on the kettle the moment it ends, we can spike up the power generation to tolerate that. They really do that, by the way. They keep track of weather, they keep track of sporting events, they keep track of major concerts, things like that, where there's going to be spikes in power when stuff changes to be able to have the grid tolerate that. That was the old way. But now as the number of power sources hugely increases, every wind turbine a different power source that has to be synchronized and managed. Every solar array, part of that problem. So we now went from a handful of power plants that had names to power all over the bloody place. They've had to learn something we've known for a long time. They've had to learn peer-to-peer networking. Look, the rest of the world, we've lived in this because we're internet people. The rest of the world is confused by it, and the power industry doubly so. But they're catching on. They've hired the right people. They're starting to get better at building a smarter grid, a grid where we can vary power rates by the hour, and we can start to have equipment responding to that, where folks that want to play arbitrage, where I'll store power now to use it later, becomes possible. That's emerging now. A few years ago when I started doing this talk, like when I did it back in 2016, we couldn't talk about this. But this is happening now. The electric car has been a stimulus to that because it's a huge amount of power, right? That's more power than your house generally uses, just because 0 to 60 in 3 is fun. And so that's where the solar panels on the roof become so important, because we localize power generation, we use it locally, and if you're fortunate enough, you're also putting a few batteries in, so you can store your excess power and use it yourself, right? You're also seeing a big push to electrify everything, to use less gas. So I bet you're getting subsidies for heat pumps just like we are in BC. You know, they want us to use more heat pumps because they've become more efficient, better than they ever used to be, and they're electricity-centric. And they represent points of discharge, which will be a part of this grid problem overall, right? We'll be able to play games with adjusting all of that. Same for the induction stove. Listen, I love gas stoves. I prefer cooking on a gas stove until you get a really good induction stove, and then you're done. You've never boiled water faster in your life. It's actually too fast. I didn't have time to go to the bathroom, right? But they consume an epic amount of electricity. So you do need your house to be wired for it. You got to be able to tolerate all that. Same for the electric car. Being able to shape when to charge. We create the EV in popular parts, and you guys are one of these folks, had that problem where everybody came home from work, plugged in their car, and started cooking food. And the grid's like, oh. Right? So we've started getting smarter now, and I've worked with some folks in different parts of the world where they actually did the math to say, does the car have enough charge to get to the nearest hospital? Yes? Then delay charging it until the rate's lower or we can distribute against the grid. Decrease the brownout stress. Charge overnight. I wonder if one of the things we're all going to get to do is to start modernizing appliances across the board. You think about an ESP32, right? They're less than $1 now. Size of your thumb, runs.net. Like, what more do you want? It actually doesn't make sense to use traditional electronics in our appliances anymore. We can do this more advanced stuff because they're actually the cheapest. So you can see a world where the power's coming into the house with a continuously variable rate, hourly or less. Your goal to get your dishes clean is not to wash them immediately. It's to be clean by morning, right? So you can basically tell it, be clean by 5 a.m. And now it negotiates for power for you. Well, when's the power going to be cheapest? After 2. Okay, that's great. And sometime around midnight, the local wind turbine kicks up and has excess power at half the price than that, and your dishwasher goes, oh, sure, I'll take some of that, and does its cycle then. You're already writing the code in your head. I can see it in your faces. This is not a hard problem for us, right? But we're not appliance makers. We're going to have to get involved in that. But when you think about a really smart grid, it's all the way to the endpoints, all of this. And I hope you feel the enthusiasm of this. We're making progress on this. The main problem with the grid right now is the variability in power. The more we can levelize that, the more dirty power plants can be turned off, and the cleaner ones can be lit up with their irregularities in it. And part of that will come with how we consume power. And I'm not asking us to be diligent. I'm asking us to write better software. So that anybody can do this. They don't need to think about it. The appliance simply does it, and you get a better rate, and your power bill is less, and we decrease the impacts we're having. I hope this was fun for you, because it was very much fun for me. It's so much fun to understand the Norwegian power grid. Thank you for your time. And the peanut gallery did nothing.